Well, welcome to week 12 in Psych 1040, and this week's lecture is about correlations. To begin with, I thought I'd go ahead and show you this interesting figure that appeared in the New York Times back in 2016. And what they were looking at in this particular article was what the relationship was between different kinds of specialties in medicine and whether or not that person was a Republican or a Democrat. So this is data collected in the United States. And you can see down at the bottom there, it's a sample of 34,532 physicians in 29 states in the US. And what you can see on the graph, if you go to the top where it says surgery, so those are just the surgeons in the sample. And then down at the bottom are people who specialize in infectious disease. And the red bar tells you what percentage of those people in that particular specialty identify with themselves as Republicans, whereas blue then would indicate that they're a Democrat. So we can see that, for instance, in surgery, 67% then of the people who responded indicated that they were Republicans, and 33% would say that they were Democrats. We go down to the bottom, you can see that psychiatry has only 24% of the specialty indicating that they're Republicans, and therefore the vast majority are going to be Democrats. So it was kind of an interesting, flash on this kind of sample that you could kind of look at whether or not political party really matters. And another way to look at this was plotted here in a scatter plot. And what they're doing here is, instead of using individuals as the person for analysis, the unit of analysis here is the entire specialty. So the entire group of people who indicated that they were that specialty. So each dot is just one specialty. That's the unit of analysis. And what we can see here is that on the y-axis, they have indicated again what the percentage of that particular profession is Republican. So you can see that, for instance, orthopedics is high over there on the far right. Again, psychiatry is down low on the left. There are not very many of them who are Republicans there. And then what we also can see is that they're plotting on the x-axis the salaries of those groups. So those are basically the median salaries of the different kinds of specialties in medicine. So you can see they don't all make the same amount of money. Psychiatrists, pediatrics, internal medicines, which would be like our GPs or family medicines in Australia, they have fairly low salaries compared to people up in cardiology, surgery, orthopedics. They're almost making twice as much money. And what this particular figure then was trying to show in the scatter plot was that perhaps one answer to why more of those people in those top specialties there are Republicans is because of their money, how much they're making. That is, perhaps it's because they make so much money that they therefore favor political issues and political policies that benefit them being wealthier, whereas the people on the left in those specialties aren't making as much money, so they're not as invested in those particular political attitudes. I'm going to come back to this, but it is an interesting set of real-world data for us to start to think about the relationships between different variables. Now, this particular scatter plot is showing us a positive relationship. And the reason why it's a positive relationship is that as the scores go up on one variable, the x-axis, like here, salary, the scores on the y-axis are also going up. So that is, the more that particular discipline makes money, the more they tend to be high in the percentage of Republicans. So they're going in the same direction, high on one, high on the other, or low on one, low on the other. And that's a positive relationship. But you could have, like I said, other patterns for the scatter plot or scatter diagram. So we could have, like I said, positive correlations, whereas one variable increases, the other variable tends to increase too. But you could have negative correlations, whereas on one variable as it increases, the other variable tends to decrease. So a negative correlation in that example would have been that if we had found that more money that you make, fewer of them were Republican, then that would be a negative correlation. But that's not what we found. We found a positive correlation. And then there's a third kind of relationship you could see, which would be a zero correlation. And that would mean that as one variable increases, the other tends to change values both up or down. So there really isn't any relationship whatsoever when you plot the two variables against each other. I should just mention, though, by the way, those are all what are called linear relationships or assessments about linear relationships. You could also have what's called a curvilinear relationship. And in a curvilinear relationship, the dots are kind of lining up more on a curve than they are on a straight line. So here's an example of a curvilinear relationship. So what I show you here is on the x-axis some sort of rating of intelligence that we have for some picture, and then you can see how attractive a person thinks that person looks in the picture. And what we're looking at is individual data from different participants. And so people who tend to see this person in the picture as being low in intelligence also seem to be finding this person not very attractive. People who are very high in ratings of intelligence also don't think the person is very attractive. But the people who kind of rate this person as being in the middle range of intelligence also seem to think the person is very attractive. So you can kind of imagine like an upside down U. That's the curvilinear relationship here. And so therefore the dots aren't like lining up nicely along one straight line. They're lining up more on a curve. And so a curvilinear relationship is another kind of relationship that you could get when you look at the scatter plot or the scatter diagram. At this point in your statistics education, we're not going to be able to talk much more about curvilinear relationships. It's more of an advanced topic, and so we have special statistical techniques to assess curvilinear relationships. So keep that in mind, that you wouldn't want to use some of the methods I want to be talking about today to analyze data if it looked like this. It was a curvilinear relationship. Instead, we're going to focus on linear relationships, where we think that the relationship could be that all the dots would be generally lining up on one line. All right? Now, these are all kind of theoretical examples that I just gave you. Let's go ahead and look at some more real-world examples from the psychology research. And I thought I'd go ahead and just share with you a couple real-world examples that come from my research group. And one of them comes from an honor students project in 2009. And it's called Measuring Collective Guilt and Other Related Emotions that Martin Henrian conducted back when he was my honor student in 2009. So Martin was really interested in this phenomenon known as guilt, and or the emotion of guilt. And he was looking at the literature and how we go about measuring guilt in psychology. And it's very common that you can measure people's guilt from self-reports. So you just ask people, how much guilt do you feel about whatever? And they rate on a scale of how guilty they feel. There's other kinds of measures of guilt, though. You can measure how guilty someone is using polygraphy and the guilty knowledge test. What happens in that test is that you would go ahead and show people pictures or words or ask them questions about a particular crime. And the idea is that if they've actually committed the crime and they're feeling kind of guilty or emotional about it, they'll have a big physiological response whenever you ask a question that's directly related to the crime. So that's kind of the whole idea behind a lie detection test. Another way, though, that's been popularized in the last 15 to 20 years is using event-related potentials to measure guilt. Now, event-related potentials means that you're going to measure EEG activity from the scalp. So you put a cap on a person's head and you measure their EEG activity, how much their brain waves change as a result of a particular stimulus. What I want you to do is pay attention to the graph on the right. That graph you can see on the x-axis is only going up to a half a second. And what we're saying is that if I go ahead and present a stimulus over and over and over and over again to you, that you'll start to have a particular brain wave signature that's always in response to that particular stimulus that will kind of take on this general shape with these different components that are bumps or troughs. That is, at around 100 milliseconds, we'll see a bump that's called the N100, then we'll see something called the P200, then we have the N200, and then we have a P300. Now the 100, 200, 300 roughly represents the amount of time that's passed since the stimulus has occurred. So you can see that we have this really big component called the P300, that we have this big response. It's somewhere around 300, 400 milliseconds in terms of when it occurs. And that is the dependent variable in this particular study that Martin used for his thesis. So the P300, that big bump that we get, happens when you notice something occurring on the screen or you hear a sound that is sort of rare. So the typical way this is studied in psychology is you could go ahead and use what's called the oddball paradigm, where you go ahead and present a stimulus over and over and over again, and then you just change the stimulus on one trial. And when the stimulus changes, it's becoming an oddball. It's different from all the other stimuli. And people will show a bigger P300, participants will, when they notice that something has changed. So for instance, if we're doing an audio ERP study, you could go boop, 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 beep. And when they hear that beep sound, they make a big P300 because they recognize that that sound is different from all the sounds that were occurring on the previous trials. That rare stimulus almost invariably elicits a P300. And when you look at the parts of the head where this would be measured, it's largely at parietal sites, so more back back towards the back of the head. And then as you move central and frontal, more close to the head, you can also see it. And it's related to how subjective you think it is. So if you think of this as a really rare stimulus, you'll see it as you'll experience it with a bigger P300. Okay, so it's not really necessarily related to how many times it really did occur. It's much more related to how the participant views how rare it is. Okay, all right. So how would this be used in lie detection or in guilty knowledge tests? So what they do is they'll go ahead and create a laboratory situation where a person can commit a crime. So the participant kind of role plays, and you tell them, go into the other room, and there's a bunch of objects in there, and I want you to steal one of them and come back and stick it in your pocket, and I won't know what it is, and I'm going to hook you up and try to figure it out. So they go ahead and put this cap on the person's head and to measure their ERPs. And the basic hypothesis here is that only the guilty suspect would see a crime-related stimulus as being deviant, and thus show P300. So imagine, for instance, that the object was a watch that they stole from the other room. So what you could do is you could show pictures of different watches. Here's a watch, here's a watch, here's a watch, here's a watch. And then suddenly you show them the watch that was stolen. Okay? Now, only they would recognize that watch as the stolen watch. So when they see it, this thing that's been stolen, they should show a big P300 because they would see it as different than the rest of the watches. If you're innocent and you hadn't touched that watch, hadn't noticed it, looked at it, or whatever, you're not going to show a big P300 because it would just look like another watch to you. So this is what I mean about the subjective probability of it. If you view the watch as being different from the other watches, then you will have a bigger P300. And that's been found in several different studies using different paradigms, that when people have some sort of knowledge of an event like this, you can assume it's related to their guilt. And it was done originally with words and then later with pictures. So like I said, it's been around for quite a while, this particular technique. Now Marty, my honor student, was interested in using this technique to measure collective guilt. Collective guilt is when a group is reminded about the transgressions committed by their other group members, past or present. So the idea is that I belong to a group, and perhaps our group as a whole has done something wrong to another group. Now, the participant may not have done anything. You, the individual who's in this group, may have nothing to do with that particular transgression, but you belong to this group that has been known for doing this thing to the other group. And what we know is that some people will feel collective guilt. That is, they feel guilty even though they didn't do anything because of their fact that they belong to this group that did something harmful to another group. So examples, for instance, would be that after World War II, a lot of Germans felt guilty about what had happened by the Nazis in the concentration camps. And so even though they themselves actually were not the people committing these crimes, even the ones that were generations later, born decades after the war, they still feel a sense of guilt, a collective guilt about what happened because their group had done these horrible things. Likewise, here in Australia, some Caucasian Australians may feel a sense of collective guilt about the way their ancestors in previous generations treated the indigenous people in this country. And so they're aware of it. They haven't done it themselves. They weren't involved in, for instance, the stolen generations, but they might feel collective guilt about it. And of course, some people don't feel any collective guilt. They don't feel any connection to this greater group guilt. And what we find in the research is that people who do feel the collective guilt generally are more likely to support reparations and other programs to help out the victims of that particular group. So what did Marty want to do? Well, he wanted to create an artificial situation where people could feel collective guilt, where he could create this in the lab. Now, he only had 24 participants, and unfortunately, Marty didn't have very much time to run this study for his thesis, so he ended up having a pretty small n, so there's not a lot of power here. He did create artificial groups. So instead of using real historical groups, he wanted to create artificial groups, and he wanted these two groups interacting where one group would do something to another group, so that one group would be the perpetrators, the people who should feel some collective guilt, and the other group would be the victims, the people who might feel some sort of collective anger about what happened to them. So in the overall, what happened in the study is that each participant went through 2 sessions. In the first session, they showed up, and this is actually a picture from one of the sessions. They were divided up into groups of red team and blue team members, and they worked together. And then a transgression happened between the red team and the blue team that would cause some sort of collective guilt. And I'll tell you about that in a moment. And then they came back a few weeks later and individually were tested with an EEG cap. And we could then look at their P300s as they were reminded about things that happened about that intergroup transgression. So what exactly happened in the intergroup transgression? Well, at session 1, as I said, participants were divided up into 2 teams, the red and the blue team. And when they worked in their own teams, they worked on something called the winter survival task, which is just a group activity to kind of create more bonding amongst the members. So the blue team would work together for a while, the red team's working together for a while. And then the final task was that each team had to create a flag. So they created this flag, and they got to use some markers and a piece of paper to do this. What they didn't realize is that the markers were water soluble, which meant that if any water got onto the paper, it would actually just blur out the entire thing, wash out the ink from the flag. All right. So anyway, they get done making their little flag. And then what the experimenters said was, okay, now I'd like you guys to meet in the middle, the red team and the blue team, and show each other, present each other your flags as kind of like a sort of like a mock sort of peace process. So you present your flag to the other side. And this is where the guilt manipulation occurred. It turned out that one of those people that was in one of those teams was actually a Confederate, a stooge, somebody working for the experimenter. And what would happen is that Confederate, during the time of the flag being presented to the other one, would accidentally knock over a cup of water that happened to be sitting on the table. So there was a pitcher of water with some glasses in case anybody got thirsty. And what he did as the flags were being presented is that he sort of accidentally knocked over the glass so that the water landed on the other team's flag. So in each session, there was just this one Confederate doing this who wiped out the other team's flag. The original team that he's part of, they're now known as the perpetrators. So even though the real participants did nothing at all to cause this quote-unquote crime to occur, they're now associated with that person who did this, and so that's why they're called the perpetrators. The other team, whose flag has been now ruined by this water spill, are now considered the victims in this paradigm. Then at the second session, he then tested each person one at a time. And at that second session, he kind of reminded them about what had happened at the last session. And then he showed them pictures of faces of different people wearing red and blue t-shirts and flags. Now, one of those faces was actually the picture of the person who knocked the water over. And one of the flags was a picture of the flag that was ruined in that previous session. So what Marty did is he had made sure he got a picture of each team's flag before they made the presentation. So he actually had a photograph of the flag before it was ruined. And so you can see this is an example of how it would work on the trials. There's actually hundreds of these trials. So you could see it'd be like flag, 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 flag. And then suddenly one of the flags is the flag that got ruined. Again, it's not a picture of it as a ruined flag. It's just what it looked like before it was ruined. So the hypotheses that were in the study was that we'd get larger P300 amplitudes for perpetrators due to their collective guilt. So we're expecting that perpetrators are going to feel a lot of guilt about what happened to that flag and show big P300s. And then we also think, though, that victims will show a large P300 for the flags sent to faces because they're going to still be very angry about the flag that was ruined. Okay, so we thought that we're going to get these big P300s for the things that happened based on collective guilt and anger. But the most important prediction was the last one, which was that we thought that for perpetrators, self-reports of collective guilt would correlate with their P300 amplitude. So what that means is that we thought that those participants who felt really guilty about what happened at the previous session, because they were in the perpetrator condition, that they'll feel guilty about the fact that this flag was ruined. And when they see a picture of the flag or see a picture of the person who did this, they're going to show a big P300 that correlates with how guilty they feel. All right, so here's what we found. So this is the actual data. So here are ERPs to probe flags. So what this is just showing you is how big the P300 is. And it turned out actually that victims had bigger P300s than perpetrators. Both groups showed big P300s when they saw the flag that had eventually gotten destroyed. But victims were showing significantly more of a P300 than the perpetrators were. So both of them seemed to recognize this is the flag and they were upset about it. But the victims were doing this more. When we showed them the faces of the people, there wasn't actually a significant difference here. It looks like the victims are showing a slightly bigger P300, but it wasn't actually a significant difference. So both victims and perpetrators, when they saw the picture of the Confederate who had ruined the flag, they were both showing big P300s to that particular individual. But like I said, the main correlation here, the one that we're really interested in, is the relationship between their collective guilt and their P300. So these again are the P300s for just the perpetrators. And on the x-axis, we can see their ratings of their self-reported collective guilt. So we can see how guilty each of those participants feels, okay? And then we can see their P300 on the y-axis. And basically, the participants who show us more collective guilt are the ones who are showing us bigger P300s to pictures of the faces, the person who actually was the perpetrator. So they seem to feel guilty when they get seen a picture of him. The ones who see him show a bigger P300, but they show even a bigger P300 if they feel guilty about what happened at that previous session. Same thing is going on for the flags as well, but they seem to be feeling more guilt when they see that perpetrator's face, or I shouldn't say they show more guilt. They show a bigger relationship between their guilt and their P300 when they see a picture of a person who was the perpetrator, okay, or the Confederate. For the victims, we also saw a correlation, but this was really about the flags. And so what you can see in this scatter plot is that the participants in the victim group who felt really angry about what happened, they felt a lot of anger towards the other group. They were the people, the ones who felt the most angry, were the ones that had the biggest P300s when they saw their flag. So even though this was just a kind of a minimal thing that happened just a couple days before, those people who are saying a few days later by themselves in this testing session that they felt a lot of anger about what happened before, they're the ones that show the biggest P300 when they see the flag. And they don't really show it for a picture of the face. Okay, so it's more about the flag. So there's our relationships. We're finding that this P300 can be used to kind of measure things like collective guilt and collective anger about something that might have happened between one group or the other. Now that's one example from my lab of kind of showing you how correlations work. Here's another one. This one's looking at a very different kind of question. And the question here was, do empathic people look more at the eyes when someone else is being emotional? And so this came out of work with my PhD student, David Cowan. And what he was interested in doing was measuring where people look with their eyes using something called an eye tracker. And what he did is he showed 59 participants 3-minute videos of someone acting sad and the same person acting neutral. So in the sad one, they kind of tell this very emotional, sad story about a death in the family. And in the neutral story, they're just talking about a time I think they were at the airport. And while they watch that video, he's able to track where they're looking at with their eyes. Now, the hypothesis here was that if you really care about another person a lot, you'll look more at their eyes than you'll look at other parts of their face, okay? And he wanted to see if your empathy that you have just as a trait, so some people are highly empathic and other people are not very empathic. He wanted to see if people who are really empathic will look more at the eyes when someone's being emotional than somebody who is low in empathy, okay? So this is kind of what it looked like. So what you see at the top is the neutral story, and that's when the woman is in the video telling this kind of neutral story about a time that she was at the airport. And what we see are examples of what a participant with kind of average empathy has, what somebody who has low empathy has, and somebody who has high empathy. And you can see that under the neutral story, they're kind of looking all over the place, a little bit on the face. That's not really where the hypothesis was predicting things. We were more interested in, do they look more at the eyes when she's being emotional? Now you can see that on the bottom, that when we look at somebody with high empathy, the lower right corner, you can see that the people with a lot of empathy are spending a lot of time just looking at her eyes. That's where they spend most of their time while she's telling the story. People who don't have very much empathy are looking at her eyes, her nose, her mouth, down at her neck. They're kind of looking all over the place. It's almost like they're not really even paying much attention to her eyes and maybe spending a lot of time looking elsewhere, okay? And then there's the typical empathy, the average amount of empathy. So we wanted to see if there was a relationship then between a trait empathy and how much people are looking at the eyes when the person tells an emotional story. So here are the actual scatter diagrams for all of these 59 participants. And these are 4 different scatter diagrams. And so what you can see is across the x-axis, we have 2 different trait measure scores. We have this measure called empathic concern. So this is a measure of how much you actually get empathically concerned about other people. And so a higher score means that this participant is more likely to show empathic concern towards other people. People who are low on that scale don't have much empathy for other people. Okay? Perspective taking is basically how much are you able to take the perspective of another person when they're telling a story. People who have a low score in that don't show much perspective taking. And what we can see is on the top there, we're looking at the amount of time they're looking at the eyes during the neutral films and how much looking at the eyes for the emotional films. And what you can see is that we get much more looking at the eyes for people who are high in empathic concern for both the neutral and the emotional stories. That's kind of interesting, is that we get this kind of relationship, but the relationship is even stronger when she's being emotional. So perspective taking seems to be kind of related to how much they're looking at the eyes, whether she's telling a neutral story or an emotional story. But the difference between neutral and emotional is much greater for empathic concern when she's telling an emotional story. So indeed, the people who show more empathy or have more empathy as just their personality trait are actually looking at her eyes more than people who don't have much empathy. And so that's what our scatter diagram shows us, a positive relationship between the participants' trait measure score and how much they behave with their eyes looking at these videos. All right, so that was a second example from my lab group showing you how correlational research might work. Here's another example, and this isn't actual data from my lab. It's just an interesting way of showing some data on a scatter plot. And what they're trying to show you here is the relationship between age, height, and weight. And also, they're showing us gender differences. So blue represents male participants, red represents female participants. And so, for instance, if you look at height, you would expect that on average men are going to be taller than women. So that's why you see more blue on the right and less so than on the left. For age, there shouldn't really be a relationship between age and gender. So in fact, when you look at that, you don't see much of a difference. But as you kind of look across the different things, you can see, for instance, that height and weight really correlate pretty well. So people who are taller tend to be heavier. You can also see that there isn't much of a relationship between age and height, right? So once you become an adult, you're not going to see that you get much taller. As you get older, you're not going to get much taller, and so on. So it's just kind of a way to sort of simultaneously look at these relationships in 3 or 4 or 9 different scatter diagrams at once. So this is a very powerful tool in psychology. We spend a lot of time looking at these kinds of relationships. You'll notice these aren't experimental in the sense that the data that we have are just looking at a couple of different dependent variables and correlating them against each other, looking at the relationship between dependent variables. So there are some caveats that we have to have when we're interpreting correlations. And perhaps the one that you've heard before, and is probably the most important caveat about correlations, is that remember that correlations do not mean that we have causality. So just because we find a really strong relationship between 2 variables, that doesn't mean that one variable causes the other. It's not been established just because you have a high correlation. X might be causing Y, that's true. So that could be the reason why you find a relationship between X and Y, is that X is the cause of Y. But the other problem that we have is that it also could be that Y is causing X. So in fact, we don't know which way is the effect. We just know that the 2 of them are highly related. And there's also another possibility. It could be that X and Y are both caused by something else, like Z. There's another variable that we didn't measure, and it might be the cause of both X and Y's changes. Or it could be just some combination of all of these things. So no matter how strong the relationship looks between 2 variables, you always want to be careful about trying to infer the causal relationship between those variables. Take, for example, again, that one that I showed you earlier in this lecture, this relationship between how Republican a particular subspecialty of medicine is and how much money they make, right? So you look at that and you say, okay, well, perhaps people who go into these professions and make a lot of money become more conservative, and that's why they're more Republican. So you could say that those professions that are over on the right, as those people started to make a lot more money, they became more Republican as a result of that. and they took on more Republican policies, found that the Republicans might be more, might have policies that are benefit them more, and so that's why they became a Republican. So it was the salary that was associated with that specialty in medicine that caused them to then want to be Republican and less Democrat. Possibility. But there's another way to look at that, right? That's X causing Y. Another way you could think of it is that maybe the Y causes the X. So maybe they were actually Democrats or Republicans first. So maybe Republicans in high school or when they're first at uni, people who are more conservative, choose specialties in medicine that make more money. And so they come from families that were already Republican, and so they go off to medical school. They pick professions that make them more money, like anesthesiology, dermatology, and so on. And so it could be that it's the Republican thing that's causing the salary, right? Or it could be maybe even a third variable. It could be a Z variable. It could be something like, let's say that you are somebody who really believes that lots of different things cause illness, and you really pay attention a lot to the environment because of that. And so when you go off into medicine, you are naturally drawn to those kinds of specialties of medicine that kind of take into account the environment. So things like psychiatry, pediatrics, family medicine have families involved. There's lots of things, other variables going on. And so you find those really interesting. And also Democrats might be people on the left that are more concerned about the situation that people are in. Whereas Republicans might say, I'm somebody who, it's not that I'm a Republican yet, but maybe I'm somebody who focuses more on the internal causes of things. I'm more interested in just like what makes people tick, and everything that they do is all internal to them. And so they're drawn more to surgery or to other kinds of medicine that don't really have to worry about the situation or the environment. And that's why they pick those. And that also tends to cause them to get paid more. And also because of their kind of beliefs about human nature, they end up becoming Republican. So I don't know. There's lots of different X's and Y's and Z's here. So just because we see this relationship between these two particular variables doesn't mean that we now know the cause. That is the important caveat that I'm trying to get across here. All right. So again, that's one of our first important caveats, but there's some other ones. Another thing that we need to remember is that what if the relationship isn't linear? I told you before that everything that I'm teaching you right now in this particular lecture assumes linear relationships between the variables, like that everything can line up on a straight line. So we always have to keep in mind that some relationships between variables might be curvilinear, and therefore, because they're not on a straight line, a lot of these analyses that we're going to be talking about today wouldn't apply. So that's another important caveat. There's also the problem of outliers, because if we get one or two people who are kind of having really high values there, they can kind of affect the entire relationship between X and Y. And you might go back to the workshop earlier in the semester where I talked about graphing, and you might remember that just having one person score different from everybody else can really change the relationship we get. And you would only know that if you made the scatter diagram or the scatter plot to see that there is an outlier. So outliers are another problem for this kind of analysis. And then there's another problem that's sort of unique to correlations, and it's called the restricted range problem. And what happens in the restricted range problem is that you end up only looking at a limited range of values, and it gives you then a misleading idea about what the relationship is or the correlation is between two variables. So here's what I mean. Let's say, for instance, that you're really interested in trying to figure out if a person's undergraduate GPA predicts their postgraduate success. Okay, so you've got a particular postgraduate program. Let's say it's organizational psychology. You got some students who have gone into org, and you want to know, is their undergraduate GPA predictive of how well they end up doing in this master's program in org psych? And so you get a handful of people, and you see something that looks like this. Here's the range of GPAs that people had, 5 to 7, and you can see how well they're doing on this measure of postgraduate success. And you might conclude, there's not really much of a relationship. It doesn't look like undergraduate GPA predicts postgraduate success. All right. Now, the problem with that is that, just looking at it the way we have it, it's possible that there is no relationship. But let's say the real problem here is that you only focused on people that had GPAs of 5 or higher. What if we go ahead and look at a much broader range? Let's just say that in some years they let people in that had lower GPAs, like 3.5, 4, 4.5, and so on. If we go ahead and include those people in, you can see now that there is more of an established relationship, that basically the higher your GPA, the more success you had in postgraduate. So what was missing before were those lower GPAs that actually also had lower success. So now by not restricting it just to people between 5 and 7 and including a broader range of GPAs, we can now see that there is a relationship between your undergraduate GPA and your postgraduate success. So the question is, can we actually quantify this relationship in a scatter plot? Is there some way that I can come up with a number that tells me exactly how strong or weak the relationship is, and maybe even tell me more about the direction? Well, the answer is yes. We can do this using Pearson's R. Now, the Pearson in Pearson's R, I want to just mention a little bit about Pearson. Interesting fellow. Now, Pearson was a statistician in his own right, but he came into our realm, our world of psychology, through this person who I mentioned before at a workshop. That's Francis Galton. You remember Francis Galton? He was this guy who's like in the middle of his life, sort of bored with different things. He had already sort of invented the field of meteorology. And he had this cousin, this famous cousin, Charles Darwin, who just published The Origin of Species. And that made Galton become preoccupied with measuring individual differences and understanding how abilities are inherited and so on. And he's the one that I mentioned to you before, coined that phrase, nature versus nurture, in his epic review of English Men of Science, Their Nature and Nurture. Because you might remember, one of the things that he believed was that intelligence was largely inherited, and he had different ways of measuring this and then showing this through his analysis of the data. Now, while he was doing that analysis of the data, that's where this Carl Pearson comes along. Carl Pearson, who lived from 1857 to 1936. In fact, there's Pearson on the left in this photo with Galton on his right around 1910. So he was, like I said, a British mathematician and biostatistician. He ended up founding the first statistics department in the world at the University of College in London in 1911. Now, I say here he's a protege of Galton. In some ways, he was sort of like a hero worshiper. I mean, he let Galton actually take credit for a lot of his mathematical work. Some of the stuff that he was doing to help Galton analyze his data, Galton just published the paper without even mentioning Pearson and Pearson's contributions. And Pearson didn't seem to mind. He seemed to enjoy being in this world of this great man. But we can see that Carl Pearson went on to develop a lot of important things here. He developed what we're talking about today, the correlation coefficient R. That's why we call it Pearson's R. He also invented the chi-square, which we talk about at the next lecture. He's the first person who really wrote about the p-value, and he perhaps even contributed the first histogram. Here's from a paper in 1895 where you can see he's actually has a histogram here where he's looking at, I think, the prices of houses in London. And making a histogram about this and having obviously a positively skewed distribution. Now, the thing about Carl Pearson that you also need to know is that he was a eugenicist, and he and Galton were both promoters of eugenics. In fact, Galton is the person who coined the term eugenics. And the aim of this field, this kind of practical field, was to improve the genetic quality of the human population, whatever that means. And so Carl Pearson, as an advocate for eugenics, wrote many essays for both the scientific audience and the lay audience, warning of the dangers of inferior races and how civilization could be improved if feeble people weren't allowed to have offspring. In fact, he was a very big opposer of letting Jewish people emigrate to the United Kingdom because he thought of them, again, as an inferior race. So there's just plenty of horrible views and policies that Carl Pearson was involved with, largely because of his work with Galton. But interestingly, he was still very popular in his time, so these were not considered such horrible views. In fact, the Queen offered him, or the King offered him, an OBE and also a knighthood. But both of these he ended up turning down because he considered himself to be on the left, that he was a socialist and a free thinker, and he didn't want to have the imperial crown there telling him what he did or didn't do. So sort of a strange juxtaposition where you think of these sort of views of eugenics as being maybe on the far right, But in fact, during this time period, a lot of people who considered themselves socialists and who were trying to improve society used eugenics as sort of the basis for what they were doing. All right. So now that you know a little bit more about Carl Pearson, the guy who's invented the statistic that we're talking about today and next week, let's go on and talk more about his actual formula. Here is the formula for the R, okay? So if we want to compute an R, what we want to do is get the sum of the z-score on x times the z-score of y, and do that for every x and every y, multiply them together, add them all up, and divide by n. All right, so you can see we're going back to z-scores here. So we want to convert each person's x and each person's y to a z-score, then multiply those two z-scores together that we get from each person's x and y, multiply them together, add them all up, and divide by n. Why are we using z-scores here? Well, because it goes back to that magical, wonderful property of z-scores. That is, it's this common language that no matter what the dependent variable was, it puts them both on the same metric. So we have a way of kind of comparing them, even if they have different ranges, they have different values. Once everything's on z-score language, everything's on a common language. And we know then that if we get a high value on a z-score, that means we have a positive z-score. And if we get a low value on our variable, we're going to end up with a negative z-score. And then when we compute the cross product, we take their z-score for their x and their z-score towards the y. Whether the two values are both high or both low will actually mean something. It actually matters. All right? So again, imagine that we take your x on how much money you make right now, and we take your y about how happy you are. Those are completely different variables, but I go ahead and convert them both to z-scores. So I know what your z-score is on how much money you make compared to everybody else. And I had your z-score for how happy you are compared to everybody else. All right? Now, if you're somebody who's really wealthy and really happy, you're going to have high z-scores. If you're somebody who doesn't make very much money, you're going to have a low z-score. And if you're not very happy, you're going to have a low z-score. All right? So imagine that we get a z-score that's positive on both of them. So a person gives us a plus 1.24 and a plus 2.0 on the second variable. You multiply those together, we get a product that's 2.48. So they're both positive, right? But imagine we have another person who's low on both of those. So they get us a minus 1.24, and they also give us a minus 2 on their y variable. Then if we multiply them together, that also comes out to be plus 2.48. If I have you're high on one and low on the other, so here you're below the mean, so you have a minus 1.24 for your x variable, but you're way above the mean on the y variable, you would give us a positive z-score of 2.0. Multiply those together, and the cross product is negative. So if the two values mainly change the same way, that is, you're high on the first variable, high on the second variable, we're going to get a lot of positive cross products. So if I add them all up across all of the participants, if everybody's kind of doing it in the same direction, we should get a lot of positive numbers. If in fact the variables are not related to each other very well, they're negatively related to each other, that is, then that would mean that if we get a lot of variables where they're opposite on one and then from the other one, we're going to get a more negative total of cross products. Okay, so when we add up all of the cross products for every single participant, so if we got 10 participants, we take the 10 people, convert them on their x variable to their z, and on the y variable, we convert that to a z. Then we multiply those things together, so each person gives us a cross product. What we'll see is if we have basically a positive relationship between x and y, we're going to get a lot of positive cross products and a total cross product that's quite high. If in fact we get the opposite, where if they're high on one, they're low on the other, the cross products will end up being a lot of them negative, and we add them all up, we're going to get a very big negative number. Okay? And if there's absolutely no relationship between the two, then they're all going to cancel each other out, and the cross products will total up to something like 0. All right? So if we go back to this definition for the correlation coefficient, you'll see that we're going to take all those cross products and divide by n. Why are we dividing by n? Well, where have you seen that before? It's like a mean, right? If we take all of the cross products and divide by n, but what we're basically doing is we're taking the sum of a bunch of numbers and dividing by n and finding their average. So really what the R is the average cross product, right? So it's saying, I go ahead and found 10 people, found their cross products for x and y, multiplying those together on their z-scores, added them all up, divided by 10, and now I have the average cross product. So if it turns out that most of them were positive, my R then is going to be a positive number. If they were mostly negative, because they were high on one, they were low on the other, then R is going to be a negative number. And if there's really overall just no relationship going on, some of the cross products are positive, some of them are negative, then when I divide them up by the n, I'll end up with an R that's close to 0. Let's go ahead and try to compute this. It's not that difficult to calculate an R. It might seem like it because there's a lot of steps, but you really actually know most of these steps now because you've had a lot of experience with z-scores in previous weeks. So let's look at this problem. Is there a relationship between the number of dogs a person owns and the number of cats that they own? And we're going to do this with a very small sample. So here's our sample. Arnie, Bubba, Callie, Donnie, Eunice, Fanny, and Gil. So we have 7 people here. And we have the number of cats that they own and the number of dogs that they own. And again, we want to know, is there a correlation between these two things? Is there a relationship? And if it is it positive or negative? Okay? So I've got the table set up. I need to know the z-scores for all the x's. I need to know the z-scores for all the y's. And then once I have each of those z-scores, I'll go ahead and come up with the cross product. Before we do that, though, let's go ahead and look at the scatter plot, or as the textbook calls it, the scatter diagram. I've gone ahead here and put red dots that represent where Arnie, Bubba, Callie, Donnie, Eunice, Fanny, and Gil are. So we can see, for instance, that Arnie has 0 dogs and 0 cats. So he's down there in the lower left. And we have Eunice, who has 3 cats and 3 dogs. So she's in the upper right. And then everybody else is somewhere else in terms of this. You can see that overall, like if we were to kind of draw an imaginary line through those dots, that it's going from lower left to the upper right. So we can kind of guess that we're going to end up with a correlation that's fairly positive, because it looks like the more cats you have, the more dogs you have, right? Again, if there was no relationship between them, it wouldn't matter how many cats you have. The number of dogs won't be related to that. All right, let's go ahead and calculate this now. So in order to convert these things to z-scores, we're going to need to know the mean for the x and the mean for the y. So what's the mean number of cats that are owned and the mean number of dogs? So I went ahead and took the sum of the x's, and it turned out to be 10, divided by the n, which was 7. So the mean of the cats is 1.43. The mean of the dogs is 8 over 7, or 1.14. So I need to use this mean of x, 1.43, to convert Arnie's number of cats into a z-score for x. So I'm only going to use the mean of x at this point. And if you go back and look at the formula for a z-score, what you do is you take the x, like here, 0, and you subtract the mean from that for that particular variable and divide it by the standard deviation. Okay? So here, what we know is that x minus the mean is 0 minus 1.43. Now you'll notice that I have given you the standard deviation. You would actually need to calculate the standard deviation as well to do this. So you don't want the s, that's the n minus 1 version of this. You want the n version of the standard deviation. So anyway, it's 0 minus 1.43 over 1.18. So I've given the standard deviation here as 1.18. And that gives me then Arnie's z-score, which is minus 1.21. So I plug that in, minus 1.21. Then if I go to Bubba, I'm going to have a 1 for his x, and 1.43 is his mean. And again, the standard deviation for x has been given to us. It's 1.18. So 1 minus 1.43 over 1.18 is minus 0.36. And I would continue, and I'll have soon all of those, right? So there's all of my z-scores. So I've just taken every x and converted it to a z-score, just like we did several weeks ago when we were first introduced to z-scores. Now you got to turn to the dogs and do the same thing there. So for the dogs, it turns out that the standard deviation for dogs is 1.13. You can work this out yourself, but the standard deviation is 1.13. So for Arnie, his number of dogs is 0, and I'm going to go ahead and subtract the mean for the dogs, which is 1.14, divided by the standard deviation for dogs, which is 1.13. And that means then that his z-score for having a 0 for the number of dogs gets transferred or translated into minus 1.01. So I put that in. I continue to do the same thing for Bubba, who has 2 dogs, and I subtract it from the mean number of dogs, which is 1.14, divided by the standard deviation for the number of dogs, which is 1.13, and that gives us then a z for Bubba of 0.76. And we can go ahead and finish this off, and we've now converted all of the number of dogs into z-scores. So you now see that we have z-scores for x, which is the z-score for the number of cats, and we have the z-score for the number of dogs. And what's missing now is what's left to do is the cross product, where I'm going to go ahead for each person, take their z-score on the x and multiply by their z-score on their y. So for Arnie, I'm going to go ahead and take minus 1.21, multiply it by minus 1.01, and what that ends up giving me then, because it's a negative number times a negative number, is a positive number, and I get 1.22. And we just keep working our way down there. We get minus 0.36 times plus 0.76, we get a minus 0.27. The next one is 0.48 times a negative number, minus 0.12, and I get a negative z-score. And I continue working all the way through that. So now I have all of the cross products. Okay, so it's really important in these calculations when you're working on your calculator that you really pay attention again to the negative and positive signs, because it will make a big difference on the cross product. We're not squaring numbers here. So here, when we multiply a negative number by a positive number, our product is going to be a negative number. You got to remember that. Or if I take two negative numbers and multiply them together, I end up with a positive number. Anyway, the last thing I need from this table is I need to sum those cross products. So I take that last column of 1.22 minus 0.27 and so on, sum them together, and we get out the number 5.67. So we now have the numerator for R. That is, it's 5.67. That's our total cross products. And because we want the average cross product, we're going to go ahead and divide by the n. So we take 5.67 and divide it by the n, and that will give us R. So there's our step. 5.67 divided by 7, and it gives us an R of 0.81. So that is our correlation coefficient for the number of cats and the number of dogs for this sample, an R of 0.81. So we now have a correlation. We've calculated it correctly. What in the world does that mean? I got an R of 0.81. We could tell from the scatter diagram that we had a pretty positive relationship. So this is a positive number. Keep in mind that R can't be greater than 1. So 0.81 gets bigger and bigger. It's going to get up to eventually 1.0 will be the upper limit. The lower limit is going to be minus 1. So R can be anywhere between minus 1 and plus 1. And it could also be an R of 0, which would mean that we'd have no relationship. So if you look at Cohen, who did a lot of the work again about effect sizes, and look at our guides for correlation, if you end up with an R of 1.0 or an R of minus 1.0, that's a perfect relationship between the two variables. If R is 0, it's nothing. There's no relationship there. So R is 0, you've got no relationship between your two variables. If R is around plus 0.5 or it's an R of minus 0.5, according to Cohen, in psychology, that would be considered a large relationship. Okay, so it's a good relationship, really large relationship when we have R of 0.5 or minus 0.5. If R is around 0.3 or minus 0.3, that's a moderate relationship. And if it's plus 0.1 or minus 0.1, in psychology, that would be considered a small relationship. So R can serve as an effect size. So as you see here, R has got effect sizes plus 0.5, plus 0.3, plus 0.1. That really maps on to large, moderate, or small. But you remember that when we've talked about effect sizes in previous weeks, we talked about Cohen and his D. And you can actually convert R to a D. So there is a formula for converting R to Cohen's D. And then once you have that, you'd see that this 0.5, 0.3, and 0.1 maps onto exactly the same numbers that are Cohen's D for a large, a moderate, and a small effect size. So the textbook shows you how to do this, and you'll want to pay attention then how you could convert an R to a D. Okay? It is rare in psychology to find a correlation that's greater than 0.4. So even though, again, it's possible to have an R of 0.5 or 0.6, we very rarely see R's that are greater than 0.4. We'll come back to that in a moment about why that might be the case. I also want to point out to you that there's also another method for computing R that you could do by hand, and it's called the raw score method. And if you were actually worried about the time and you were trying to figure out the correlation coefficient, this is actually faster than going ahead and finding out the standard deviations and converting everything to z-scores and the cross products. What this formula is doing is it's just saying all you need to know is what the x is, what the y is, the sum of the x's, the sum of the y's, and then look at x times y and so on. And once you do all of that, you've got all those x's and y's and xy's and x squares and y squares, which are much faster to calculate in your table. You look at their sums, you can plug them into this formula, and you'll end up getting the same r as you would have if you had gone ahead and done it the way that I showed you with the definitional formula. So far we've been focusing on computing R as a sample statistic to describe the relationship between the variables within our sample. What about hypothesis testing? Can we do that? Can we make inferences about what the relationships might be like out in the population? In order to do that, I want you to, again, pay attention to our notation here. It doesn't come up there that often because most people just use R all the time. But R is really a sample statistic. So it is this measure of association between two variables within a sample. And if you were then to think about what this would be like in the population, well, you would use the Greek symbol as a population parameter. That's sort of like a cursive looking P. It's a Greek symbol that we pronounce as rho. And so the idea here is that we would use our sample statistic R to make inferences about a population parameter rho. Okay? Now, when we're doing our hypothesis testing and we're thinking about this population parameter rho and basing it on our R, it turns out that these R, or these rho distributions, if you were to look at them out there as sampling distributions, they actually follow the shapes of T distributions. That is, they're affected as well by degrees of freedom. And since there are estimated parameters in our R, or our rho, that means then that the shape of our underlying comparison distribution changes based on the degrees of freedom. So over on the left, I'm showing you here an R distribution. This is what it looks like. You can see it looks like a normal curve, but it's not necessarily a normal curve because it depends again on what the degrees of freedom are. Over on the right, you can see there I have my T distributions with different degrees of freedom. And you might remember that, as we increase the degrees of freedom, the T distribution becomes closer and closer to a normal curve. So again, this makes much more of a difference when we're using smaller samples. When our degrees of freedom are smaller for R, then we're going to need to depend much more on this T distribution to help us make inferences on our comparison distribution. So what we'll be doing actually when we do our hypothesis testing here is we're going to convert our R statistic to a T statistic. Kind of like the way we did this with means, we did this when we did this with Z-scores. We're just going to use this, make a transformation of the R to a T. And then once we have it in a T, we can then look it up in a T table and make sense by making comparisons to a T distribution. So to determine whether a correlation is significant, what we do is we convert the R to a T using this formula. So where I put the R in the numerator, and then in the denominator, you can see I have the square root sign, and everything underneath there is brackets 1 minus R squared, brackets, then I have a divided symbol there, and then n minus 2. And it turns out then that degrees of freedom for an R is n minus 2. So this time it's not n minus 1. For an R, degrees of freedom is n minus 2. So once I've done that, I've converted the R to a T, and I know that I have degrees of freedom of n minus 2, I can then use this to help me figure out where is the critical value in my comparison distribution and decide whether or not my correlation is significant. So let me walk you through an example here where we have our 5 steps of hypothesis testing, okay? So let's start with this example. Suppose a researcher is studying the relationship of sleep to mood, and there are 6 participants in the study, and they're asked to indicate the number of hours that they slept last night and how happy they are right now. And we won't bother to go through the whole calculations again of an R because we just did that a little while ago. Let's just assume, though, that the researcher calculates that the R is 0.85. So that's a pretty high correlation. Now, let's go ahead and walk through the 5 steps of hypothesis testing. So step 1 is always to restate the question as a research hypothesis and a null hypothesis about the populations. Well, population 1 then would be that we say we drew people who are like those in this study. Population 2 would be people for whom there is no correlation between the number of hours they sleep in the night and the mood the next day. So the null hypothesis would be that rho is equal to 0. That is, for population 2, that this would be the typical kind of population. There is no relationship between the number of hours they sleep and what their mood is the next day. So rho is equal to 0. If we can reject that null hypothesis, then we're going to adopt our alternative or our research hypothesis, which is that rho is not equal to 0. I'll point out that you can again have directional hypotheses here. So you could predict that the relationship is positive or the relationship is negative. But for now, I'm going to do this more like a two-tailed test again, where I'm going to go ahead and say it could happen either direction, just that it's not equal to 0. In step 2, what I'm going to do is determine the characteristics of the comparison distribution. Now remember, for hypothesis testing for R, our comparison distribution of rho, or the P or the R, is actually taking on the shape of a T distribution. So really, our T distribution becomes our comparison distribution with n minus 2, and in this case, that would equal 4 degrees of freedom because we had 6 participants minus 2, and it's 4 degrees of freedom. Now remember, we do this because the correlation distribution is our comparison distribution, but that it follows the shape of T distributions. So that's why we're back to using T again, at least for these couple steps. Step 3 is to determine the cutoff sample score on the comparison distribution at which the null hypothesis should be rejected. So this is where you would look, if you're doing this by hand, to a table like this, like our table 2 here that I've made available up on Blackboard of T values. And if I pick that middle column there where I have a two-tailed test of 0.05, and I go down that column until I get to degrees of freedom of 4, because remember that's what my degrees of freedom are in this problem, 6 minus 2, 4, I can see that the cutoff is 2.776. So a T of plus 2.776 or a T of minus 2.776 is the place where if anything is greater than that, I'll decide then that I can reject the null hypothesis. Step 3 is then 0.05 level, two-tailed, degrees of freedom of 4. My T that's needed is plus or minus 2.776. My next step is to determine my sample score on the comparison distribution. So this is where I just gave you that new formula, the one where I convert an R to a T. And so you can see that's what I've been doing here. I'm actually doing it all on one line. But in order to find the T, I go ahead and plug in the R that I got from this sample, which was 0.85. And then I divided it by the square root of 1 minus 0.85 squared, divided by 6 minus 2, which would be 4. That's all in the denominator. I go ahead and take the square root of it. So I get 0.85 divided by the square root of 0.0694. And that gives me then a T in the end of 3.23. So all I did was I took that R formula to T, converted my R to a T, and got a T of 3.23. That's step 4. Then number 5 is take my score at step 4, my T of 3.23, and compare it to my cutoff at step 3, which was 2.776. So yes, it's more extreme than 2.776, and so therefore I'm going to reject the null hypothesis. The research hypothesis is supported. There is a significant relationship between the hours of sleep and the next day mood for people in the study. And I can even say it's a positive correlation because I did actually get a positive R. All right, so those are my 5 steps of hypothesis testing, how I determine whether or not a correlation is significant. And again, I'm doing this all by hand. If you do this in Jamovi or in some other statistical program, it will find the R for you, and it will tell you again what the probability is of getting that R directly. So you don't have to actually do any of these conversions to T and so on when you use a computer. How you report a correlation in the text in terms of APA style, what we do is we usually write this in the results section, and then we interpret the statistics in the discussion section. So when we're reporting a correlation in the results section, we'd either make a table where we'd report a correlation matrix. So we might have a whole matrix of all of the possible combinations. Or I could write a sentence that just reports the correlation, where I could say something like, we found a negative relationship between shyness and the number of miles students traveled to attend the university, comma, R, there's my R statistic. In brackets, I put the degrees of freedom, 58. So that must mean that in this particular problem, I had 60 participants, n minus 2, 58, equals, and there's my obtained R, minus 0.67. So again, I could get that from the computer. I could get that by hand by calculating it. And then P less than 0.05 tells me that this is a significant effect at the 0.05 level. So I have a significant relationship between these two variables. And then in the discussion section, that's where you actually go on and interpret your findings. You could say something like, the negative relationship between shyness and the miles traveled to the university was consistent with our hypothesis. Students who are more shy are probably reluctant to travel far from their families and friends when a desirable alternative is closer. On the other hand, students low in shyness might view attending a university far from their hometowns as an opportunity to meet new people. Now, the sizes of correlations, what do they mean? To compare correlations directly across different studies, you can compute what's called the coefficient of determination by squaring the R. So if you take an R and you square it, so you take 0.2 and you call it R squared, you see that it's 0.04 is the coefficient of determination. And then if I go ahead and have another one and I say R is equal to 0.5, I want to square it again, and to square it, I'll end up getting a number 0.25. Now you look at that and you can say, why did I just do that? Well, in order to compare correlations directly, you want to use coefficients of determination. So in fact, the relationship that we see, the second relationship here, is a little over 6 times greater than the first relationship. Why I say that is that you'll notice that the R's were only 0.2 and 0.5, so you could say, well, it looks like the second correlation is just a little bit twice as much as the first. But the actual comparison is going to be based on R squared. And you can see that 0.25 is about a little over 6 times greater than 0.04. So that's why we can say that the correlation here is 6 times greater than the other correlation. That's a much, much bigger correlation to find one of R of 0.5 than it is to 0.2. The reason why is it's really telling us R squared is what's called the proportion of variance that's shared between the two variables. So R squared tells us that X and Y share this much variance, like 4%, 25%, 0.79, okay, whatever it is. And then that becomes the metric in the way that we compare different correlations to see how big they are. It's by squaring them using R squared, this coefficient of determination. You can also use Cohen's guidelines, of course, to make sense of your correlations. But you might remember that I told you it's pretty rare in psychology to find correlations that are much greater than 0.4. Why is that? Why is it so rare to find an R greater than 0.4? Well, let's consider that a little bit. What's going on in psychology and other sciences? One of the things that we know is going to determine how big the correlation is how much measurement error there is. And so, for instance, think about just measuring height versus shyness. Which one's more reliable? Measuring someone's height or measuring how shy they are? Now, I hope you could figure the answer there would be height, right? Shyness could be a pretty unreliable measure. It could be that today you're feeling a little bit more shy. A few hours from now, you're a little less shy. So depending on the time of day I measure your shyness, it could change a little bit. Your height, not going to change, right? So if the variable that we're measuring has a little bit of measurement error, has a little bit of variability, like for instance, depending on what time of day it is, maybe how well you read the questions, whether you're tired, anything like that that contributes to measurement error means that we're going to end up getting a smaller correlation. So that is one of the answers, is that a lot of the variables that we're measuring in psychology have a certain amount of measurement error associated with them just because they are really difficult to measure. We don't have nice physical measures sometimes, like the way you can measure height. Another reason why that we might not get a correlation much greater than 0.4 is that no one correlation can really tell the whole story. That is, even if X is causing Y, it could be that X isn't the only cause of Y. It could be other things that also cause Y. So for instance, shyness might be the cause of why people go off to university where they go, but there's other reasons why they go to their university, why they pick it. It could be because of money. It could be because they've got a sick relative. So there's lots of reasons why people go off to uni. And if we find that, for instance, shyness is one of the reasons, then it's not in itself going to be a big correlation between shyness and how far away you've traveled to go to university. So again, in psychology, we're usually looking at multiple variables causing changes in behavior. So there's a lot of things that are determining our behavior, not just one variable. And so when we have multiple variables causing changes in our behavior, we psychologists are pretty excited when we can find one that accounts for some part of this whole equation. So we're pretty happy when we can get a small or a medium correlation. Even though it's not accounting for a lot of the variance, it's accounting for something. We've got some part of the puzzle worked out. And hopefully we can keep trying to identify more and more of the variables and put them all together. When we have a relationship between a variable and another variable, we can use that relationship to make predictions. And making predictions like that is what's called regression. So simple linear regression is when we have one variable making a prediction to another variable. And then when we want to go ahead and use multiple variables to make that prediction, because maybe we've done some more research and found that this variable is also related to my other variable, I can start putting them all in together, and that's called multiple regression. Now, we're not really spending much time in this course on linear or multiple regression. So regression is a topic that we save for other years in our research methods courses here at UQ. But I will just tell you a little bit about regression just so you can get a bit of an understanding of what I mean here. Now, you've actually been exposed to regression already because we were looking at a lot of scatter plots. And you might remember that in a lot of those scatter plots, there was a line that was drawn through the scatter plot. And so, for example, when I was showing you a positive correlation here between ratings of intelligence and attractiveness, I could have added a line like this that's called a regression line. And you'll see this a lot in scatter plots. And for instance, Jamovi does this almost, I think, by default. So you can see that a line gets drawn through here, and that's the regression line. Now, why did I draw the line like that? The line is sort of like my best estimate, right? Where the relationship actually is. And what I can do then is, once I have a line like that, is use it to make predictions about future variables. So for instance, if I have another person who has a intelligence score of 5.5, I could look on that line where attractiveness intersects 5.5 and maybe then make a judgment about what I think attractiveness should be based on that regression line. So what is a regression line? Basically, it's a straight line that appears to come close to minimizing what's called the square deviations between the height of the points and the line. So you can see how all of those dots are sort of scattered along that line, but they're not exactly on the line, are they? There's some of them that are further away and others that are close by. And let's just say, though, I could have drawn, and let's have another relationship here. Let's say I look at this relationship between the amount of sleep that I got and how grumpy I am. And you can see that the amount of sleep that I have going up is showing that my grumpiness goes down. So I have a negative relationship. And what all of those observations would be all the different times that I've recorded how much sleep I've had and how grumpy I was the next day. And you can see that generally there's this negative relationship, right? And I've drawn the line there on the left to be the best fitting regression line, whereas the one on the right would not be a very good regression line, would it? You can see that line seems to really miss a lot of the dots. So that's not really a good fit for the regression line. Now, when I mean fit, and I'm kind of eyeballing it all here, there is a way to precisely measure how good the line is. So the way you do that is you figure out how each observation that you have in your data set differs from that line. So that's a deviation. So you can see here, I've connected little lines from each point that was observed to the regression line, and then I can measure that distance and then record it and square it. And that would be my squared deviation. Whereas the one on the right, because the line is so far off where most of the cluster is, you can see that I get some really big deviations, right? So over there on the left, you can see that around 5 or 6 hours of sleep, this line is so far off that I would get a very large deviation, giving me very large square deviations. So what happens in regression is the best line, the estimate that comes closest to minimizing those deviations as much as possible. So you might remember that a line has this as its formula, that y is equal to a plus bx. And so if I want to figure out what an x is to the y, I need to know what a is, which is the y-intercept, the place where when x is 0, where does it cross at the y? And then b is the slope of the line, how much it changes for each unit of x to the y. Well, in regression, the slope of the regression line is called the regression coefficient. And therefore, we can compute the regression coefficient, we can compute the y-intercept, and then we would have our regression line. Our regression line then is the best fit, the one that has the least amount of square deviations. To do this, we can use Jamovi and SPSS or whatever else to find regression lines. And Jamovi will precisely tell you what the best line is and give you that slope and that y-intercept, that regression coefficient and y-intercept. Let me show you how. All right, so I'm in Jamovi, and I've opened up a file that comes from Navarro and Foxcroft's book on learning statistics with Jamovi. In this particular dataset, we have Dan's sleep, Dan's grumpiness for each day, and you can see that in the far column there, it says day 1, 2, 3, 4, 5. So these are all the different observations for different days of Dan's sleep and Dan's grumpiness. And then you can see how much Dan's newborn baby was sleeping that day. So how much sleep did they get in total? And what we've got over on the right are histograms that I've drawn using a different histogram module that I like here on Jamovi from JJ Stats Plot. And you can see that for the first one, which is Dan's sleep, the mean is around 6.97. Looks like pretty much like a normal curve. The baby's sleep is mean of 8.05. So the baby's definitely getting more sleep than Dan is. And finally, we have the last variable, which is Dan's grumpiness. And we can see that that's got a fairly normal distribution as well. So on this rating scale about how grumpy he was, it was a mean of 63.71. To look at correlations in Jamovi, what you do is you go up here to regression and you click on this and you can get this choice here of correlation matrix. So you pick correlation matrix, and then immediately what we can see is that we can now pick which variables we want to look at in terms of correlation. So what I can do is I can pick the number of hours that Dan has slept each day, the number of hours that the baby slept that day, and then how grumpy Dan is. And so what you see down now in my correlation matrix is what the correlations actually are. And what I've done is I've just gone ahead and tested them, the hypothesis here that they're correlated or not, so not a particular direction. You can also see here that I asked it to report the significance. So I've got the p-values here. So each of these correlations is actually significant, and they all are significant at p less than 0.001. So if I picked 0.05, I would definitely be significant here anyway. So what do we see there? That the more sleep that Dan gets is related to more sleep that the baby gets, and that when Dan gets more sleep, his grumpiness goes down. That's the minus 9.9 correlation. And when baby sleeps and Dan is grumpy, that's also a negative relationship. So the more sleep the baby gets, the less Dan is grumpy. So you can see that all just in the correlations. If I pick plot here, I can also get my correlation, my scatter plots. And what you can see here is just the way it's drawn it in Jamovi is I can kind of get the intersection of here is Dan's sleep and baby sleep. And so you can see that that's a positive correlation. Dan's grumpiness is negatively correlated with how much sleep he gets and how much baby gets sleep. The line that you see there is the regression line. And that little cloud there is kind of telling us about the error around the line, which again is something that comes along more when we talk about regression. So it's more of an advanced topic, but that's basically sort of like a standard error, if you will, like a way of telling us how much error we have along the regression line. Now, notice that we aren't getting the actual information to make a regression line here. So in order to do that, I go back up here to regression and I pick linear regression now as a choice. And when I pick linear regression, it's going to ask me, what's the dependent variable? What's the thing that I want to predict to? Let's say we want to predict to Dan's grumpiness, okay? And the best predictor for Dan's grumpiness might be how much sleep the baby gets. So I put that in here as a covariate. And so now what's happened is down here in the linear regression, you can see that I have some coefficients listed. It says intercept. So that is going to be equal to, y equals mx plus b. That's the b part. That's my y-intercept. So 85.78 is what I would put as my intercept for my y-intercept. And then the slope, or the regression coefficient, is that number that you see there. It's estimate, minus 2.74. So I now have the formula for the line to make a prediction about Dan's grumpiness from baby sleep. These two numbers down here, this one represents the regression coefficient, this one represents the y-intercept. But basically, it gave me the best line that it could based on the information that I gave it. You can see there's a lot of other choices here. And again, when you get into regression, I think probably in your third year, you'll get to know more about these things and what they all mean. But you're, of course, welcome to open these things up in your Jamovi copy and try them out and see what they mean. All right, so that wraps up our discussion of correlation, and we even had a little regression in there. So next lecture will be our last lecture for this course. It's going to be on another one of Pearson's inventions, the chi-square test. I'll see you then.